Good morning. Welcome to module 12 on acoustic phonetics, which is Oropharyngeal chamber as an acoustic filter. As we described in the earlier modules, we talked about source and filter phenomenon, and in the previous module, we looked at some of the essential basic properties, acoustic properties of the source. Source of voice, source of sound, and that is voice and its acoustic properties. In terms of its acoustic properties, we talked about the fundamental tone and harmonics. To begin with, the Oropharyngeal chamber as an acoustic filter, as a selective filter, we may just revisit very briefly the articulatory and the acoustic phenomenon together. 4 processes of speech production in conventional articulatory terms are airstream process and phonation process 1 and 2, oronasal process and articulatory process as number 3 and 4. Then 1 and 2 covered in the acoustic transmission, let's say source filter theory, processes 1 and 2 covered in the source, which is larynx as the source, and oropharyngeal chamber as an acoustic filter. Whatever processes we cover in that includes 3 and 4 above. These 3 and 4 processes are modifying the oral configurations in so many different ways that the airflow through this air column gets modified in different ways to produce different sounds. So in this unit, we are looking at the filter phenomenon, and very briefly, source filter theory, once again to mention, was proposed by Müller in 1848. This was developed and extended to a comprehensive theory by Hermann in 1944, Fant in 1960, Lieberman and Blumstein in 1988. So a number of people have been working on source and filter theory, meaning the acoustic theory of speech production. Fant, 1960, he again presented a comprehensive account of his source filter theory, and this is now referred to as linear source filter theory of speech production. Now, this entire thing is dependent on filter phenomenon, which is the oral chamber acting like a selective filter. In order to understand what is filtering, we must first understand what is resonance. Just look at this picture before you on the slide, where oropharyngeal chamber, meaning after the glottis, supraglottal chamber, from there through the pharynx going into the oral chamber, the air stream is passing through a continuous air column. Now this air column, if you remember the articulatory definition of vowels and consonants, you will recall that if there is no obstruction in the mid-sagittal section of the oral chamber in the flow of air, then no obstruction would produce vowel sounds. If there is an obstruction somewhere in the mid-sagittal section of the air column, then consonants will be produced. So consonants are plus obstruents, vowels are minus obstruents and plus continuants. So that is the articulatory phenomenon. So here, just look at this picture. Through this continuous air column, the airflow is continuous. And if it is continuant, meaning the air column is providing that kind of a passage to the glottal tone, then depending on the size and the shape of the air column, resonances are bound to happen. So that resonance in a continuous air column is a phenomenon which we have to understand. Resonance would mean certain frequencies will find resonance, will be amplified, and therefore they will stand apart, stand out clearly. And those which do not find any kind of amplification, they will die out or they will be filtered out. So that is the resonance and the filter are the opposites of each other. So diagrammatically you can represent that this is from another source. The source is mentioned there. The glottal source or the sound source is the first box showing this is the source of the sound, and then supraglottal source leading to a certain, the phonated airstream leading to the second box, which is vocal tract filter. So the source and the filter together leading to production of speech sounds. So this is a very simplified version of source filter mechanism. Now, in order to understand, going back to the phenomenon of resonance and filtering, just look at these two pictures before you. One is a straight air column, which is a flute, our traditional bansuri. A long air column, straight air column, but the obstructions are provided by these little holes. Some of these holes may be covered or uncovered depending on what kind of configuration you want, what kind of air columns you want. And the other one is a trumpet. Trumpet looks much more complicated. And just take a look. It has not just a thin pipe leading to a gradually broadening air column at the other end, and towards the end it's a very big kind of an air column. So what I want to show you here is the air column may be a straight continuous air column leading to one kind of frequency, natural frequency, and that natural frequency will find resonance. Some frequencies will be picked up and that will find resonance if the phonated airstream passes through that. But in case the air column is modified in between, as you move from one end of the air column to the other, you find that there is a bend, there is one bend, and then the second, then the third, and the fourth, and trumpet is showing, at least so many, 1, 2, 3, maybe 5, 6 or 7 different kinds of air columns which are quite different from each other. All of these 6 or 7 air columns, because of their size and shape, that configuration, they will have different kind of natural frequency. And that frequency will be picked up for resonance as the phonated airstream, as the sound passes through these columns. A trumpet will have at least 6 or 7 different frequencies which are resonating. Similarly, a flute, if you don't cover any of these holes, then all of these holes will provide, an equal small chambers, small chambers here. But if you cover, 2 or 3 holes and then see the chamber sizes are modified. Okay. So, like this, the air columns can be very good resonators, and resonance in the air column is the basic thing that we need to understand if we want to understand what is happening in the oral chamber. Now, the oropharyngeal chamber is like a bent pipe, and in this picture that you can see before you, this bent pipe shows one major modification at the turn where the air flow goes straight up and then turns to, through the oral chamber. And that is where we have written 1 and 2. The first air column is a large air column, the pharyngeal air column. That's a large air column. This will lead to a small frequency as its natural frequency. So the resonance will be much smaller here. The second air column is smaller than 1, therefore the frequency, natural frequency will be higher. Then the third air column is the smallest, which is after the tip of the tongue and between the teeth and the lips. So that is the third small air column. The smallest air column will lead to the highest natural frequency, and that frequency will be picked up for resonance. So three different frequencies will show resonance because of this kind of an air column, oropharyngeal chamber as a resonator. Now, since it is picking up certain frequencies for resonance, it is called a selective filter. The rest of the frequencies are filtered out. And these frequencies are since it is a large air column, there you will have certain bands of frequencies picked up for resonance. So the first band of frequencies which shows resonance in the first air column is the first formant. The second band of frequencies picked up for resonance will be the second formant, and the third band of frequencies, if there is an air column between the teeth and the lips, then that is the third formant. These formants, as bundles of resonant frequencies, they define all our vowels, all our vocalic articulations in acoustic terms. So this oropharyngeal chamber as a selective filter, as a resonator, is extremely, this is a very oversimplified kind of a picture showing how the air column can modify the airstream passing through this. Now here is a formula before you, Fant formula, for working out the values of the three formants. Now this is F is a formant, and which is this formant? 2 multiplied by I representing refers to the number of the formant, whether it is the first formant or the second or the third. It could be 1 or 2 or 3. Now multiplied by I and then minus 1. You take this figure and multiply the whole thing with what you see in the brackets, velocity of sound divided by 4 times the length of the air column. So as you can see, the length of the air column, which is very different in different human beings, so that plays one role. Velocity of sound is another feature. And then whether this is the first formant or the second formant or the third formant, because we know the first, second and the third, they are different in size and shape and so on and so forth. So taking 17 centimeters or 0.17 meters as the average length of the male oropharyngeal chamber, you can convert these into numbers and see what you get. 2 multiplied by 1 for F1, 2 multiplied by 2 for F2, 2 multiplied by 3 for formant 3. Then minus 1, and the whole thing is multiplied by 340 meters per second is the velocity, and then divided by 0.17 meters into 4. The figures that you get as a result of this, the F1 at 500, F2 at 1500 and F3 as 2500. These are the formant frequencies, the first formant frequency, the second and the third. And all of this is happening in the normal, natural rest position of the tongue. And that, just let me remind you, that is the articulatory configuration for sure for vowel A. So the formants for vowel A are F1 500, around 500, F2 around 1500 and F3 around 2500. So similarly, now if we have, in case of schwa, this is the normal natural rest position of the tongue. This position, this configuration will change. In case of a high vowel, the tongue will rise higher. In case of low vowels, the jaw and the tongue will move lower to make it an open vowel, A or O or A. Or E or U for the high positions of the tongue. So with those modifications, the F1, F2 and F3 values are bound to change. So this is one picture taken from La Defogate 1962, and this shows 8 different words of English, starting with heed and head and then going over to the back vowels. The last one would be who would, meaning from E to U, the entire cardinal vowel picture is covered. And you see the articulatory configuration changes, and on the side you have spectral peaks, the resonance peaks, and they define the acoustic product that is produced in this oral configuration. So as we come to the vocalic versus consonantal, I would like to remind you that the inarticulatory terms, plus minus continuant is the definition for vowels. That defines the vowels. It has to be a continuous speech sound, continuous airflow, and minus continuant will be a consonant. Similarly, plus or minus obstruent. Plus obstruent would be a consonant, minus obstruent would be a vowel. So with these kinds of definitions, we are now looking at the acoustic properties, bringing in resonance as another binary feature, the most important binary feature in acoustic terms. So plus minus resonance will again define some of these vocalic and non-vocalic or consonantal sounds. So vocalic sounds in acoustic terms, vocalic as a category including vowels and a few other sounds. Vocalic sounds are those high energy resonant sounds which have acoustic field well organized in the form of formant patterns. Consonantal, the feature consonantal plus minus consonantal is defined as plus consonantal is low energy sounds. So minus consonantal would be high energy sounds. With these kinds of parameters, we should be able to arrive at some kind of a classification with vocalic and non-vocalic, consonantal, non-consonantal sounds, and the major class features and 4 major classes of speech sounds. I'm sure you are familiar with those through phonetics or through phonology, that we can use these 2 features. Plus vocalic, minus vocalic term parameter can also be replaced by plus resonant or minus resonant, because resonance has led to the acoustic field being organized in terms of formant patterns, So you can call it plus resonance or minus resonance. You can also replace it by the other feature, which is an auditory correlate, which is the sonority, plus resonant, minus resonant, and so on. In any case, plus consonantal continues to be low energy sounds in acoustic terms, and minus consonantal should be the high energy sounds. Now, as we continue through oropharyngeal chamber as an acoustic filter, we would also like to look at spectrograms to study the formants and also perhaps the voice quality, F0 and harmonics. Now, what we have seen earlier, we tried to explain what is a spectrogram, and what we can see there is that all the three major parameters of sound waves, the time and frequency and intensity, are taken care of in a spectrogram. So spectrograms for formants 1, 2 and 3 will show you the time on x-axis, frequency on y-axis, and frequency scale will show you where the resonance is happening, and therefore you will see dark bands of frequencies with high intensity because of resonance and so on, and lighter bands of frequencies, meaning these frequencies are being filtered out. So now we have two kinds of spectrograms there, the wideband spectrogram and the narrowband spectrogram. The wideband spectrogram, as the term shows, you can use a wide, a broad filter. you can use a filter of, let's say, 300 hertz something, then what you will get is a wide band spectrogram. As you can see in the first spectrogram, the formants can be clearly seen. The F1, F2 and perhaps F3 and some higher formants can also be seen. The upper frame in both the pictures shows the oscillogram or the waveform, and that is not a spectrogram. For that sound, the lower frame shows the spectrogram. So wideband spectrogram on your left is showing, which is produced with the help of, by choosing a filter, choosing a 300 to 350 hertz filter. You get these wide bands, and these are the formants F1, F2 and F3s. If you choose a narrow filter, then interestingly, the conventional spectrography was, choose a filter and produce all your wideband or narrowband spectrogram. But we used to make use of this narrowband filter primarily to identify the harmonics. If you choose a narrowband, something like 45 to 50 hertz as the filter, then it scans all the frequencies very narrowly, very closely, and what you get is the 45 hertz filter will give you a narrowband filtering, narrowband spectrogram, and through this you can identify the fundamental tone and the harmonics. So what happens is, since all the harmonics are the whole number multiples, as you can see in the picture, if from the first harmonic you cannot read the difference between, let's say, 200 hertz and 210 hertz or 220 hertz. 10, 20 hertz you can't really figure out there. But if you go to a higher harmonic, maybe 10th harmonic, 10th harmonic will be not 200, but it will be 2000. So 2100, 2200, those hundreds can be easily identified. So if you look at the 10th or the 20th harmonic, if the 10th harmonic is at 2150, then divide it by 10 and the fundamental tone is 215 hertz. So you get the finer, more precise result if you look at the higher harmonic. Anyways, now the computer does it all for you, and it gives you the fundamental tone and the basic pitch variation, even up to 2 hertz or 1 hertz or point something and so on. But this is the exercise. I mean, how to decipher this kind of a spectrogram? You can take a look at the picture and look at the harmonics. So narrowband and the wideband spectrograms. You can produce a wideband spectrogram, and a red line running through this will show you the pitch variations, and you take your cursor to that level and it will show you how much is the up and down or variation in the pitch level. So things are now much simpler with computer-aided programs and softwares. Thank you very much.